Hello students, let us understand combinations of class 12. Earlier lesson we have seen permutations. In continuation we are seeing now combinations. Let us see. So if certain objects are to be arranged from a set of objects, if the order is not important, then it is concept is combination. If the order is important, then concept of permutation. What do you mean by order is not important? That means this is a set of items. Suppose in a set we have 1, 2, 3 elements. 1, 2, 3. So you put it as 2, 3, 1, 3, 1, 2, 3, 2, 1, all are same. As far as combination is concerned. So order is not important. In a permutation, 1, 2, 3 is different from 1, 3, 2. Like a dictionary order. 1, 3, 2 is different from 3, 2, 1. So this is R factorial ways. This is more times. Permutation is R factorial times, more times than combination. R factorial will merge into one combination. So we have seen earlier in permutation, selecting of R items from N items is NPR, which includes R factorial permutations. So from this itself we know the combination is R factorial permutation lead to one combination. So it is by R factorial. NPR by R factorial is the number of combinations of selecting R elements from N elements. So this R factorial permutations will be reduced in combinations. So NPR by R factorial. We know NPR is basically 10 into n minus 1 into n minus 2 up to n minus r plus 1. That we have designated as factorial n by factorial n minus r. So once I divide with r factorial, so factorial n by factorial r by factorial n minus r is equal to NCR. So this is the, suppose I want to select n items, total items. Instead of r, all n items I have to select. N of n items. Then we know permutation is n factorial. Permutation is n factorial. I can arrange n items in n factorial ways, but combination is only one. Because all n items, once I group together, it is only one way I can group them together. There is no item is left over, no additional item is added. So this is combination is one. But same thing I have arranged in n factorial ways in permutation. So here also we can see combination is permutations by n factorial. N factorial by n factorial is 1. So selecting all n items out of n given items is only one way. All are included. Only one possible way. So this also is proving that combination is n R factorial division. So same is the formula appearing. See, NCR is n factorial by R factorial n minus R factorial. We can also write this as n minus R factorial into R factorial. We can interchange n minus R factorial first, R factorial later. Then this can also be said as NC n minus R. So that means NCR and NC n minus R both are same only. Because in the combination, either n minus R factorial is only interchange. Okay, let us see some small example. I want to select 6 elements sets, subsets of 6 elements from 10 elements. I want to make a groups of 6 elements out of 10 elements. So I have, it's not 10 elements is a set I am making. Set means combination. So 10C 6. This is, suppose it is 8 elements. It's even 10C 8. That means it is 8 elements. 10C 8. That is the, when I do that, NC8 is 10C2, NCR is NC n minus R. So 10C2. So 10 into 9 by 2 factorial. I'm getting whatever subsets are possible. Okay. Now, suppose at least 6 from 10. Here is 8 elements. Here we are talking of at least 6. So it can have 6 elements one set, Another set can have 7 elements, 8 elements, 9 elements, like that. So we have to add all the possibilities. For 6 elements, it is 10C6. For 7, it is 10C7, 10C8, 10C9, 10C10. So many subsets I can make from at least 6. So at least 6 means 6 and above. So I'm taking 6 group in so many ways, 7 group, 8 group, 9 group, 10 group. And add all these, I'm getting 386. So these are the two small examples we have given here to understand what is NCR. So only 8 elements, NC8. At least 6, so 6 to 10. This is let us see some formulas of combinations. Keeping it here. Okay. Let us say there are n objects and r objects to be selected. I want k particular objects to be always included. K to be included. So out of n, k is already selected. Out of r, k is already selected. So what balance I have to select? N from n minus k, I have to select r minus k. So n minus k, c r minus k is the number of ways because k is already selected. K particular objects are never selected. That means I have to select r objects out of which k objects should not be there. So what is the leftover for it? From which lot it has to be selected? It has to be from n minus k. From n minus k I have to select r objects. So this is n minus k c r. So in terms of 1 k, if I put 1, so one object, one particular object, then what it is becoming? N minus 1 c r minus 1. This is n minus 1 c r. C1. When I put k is 1, n minus 1 c r minus 1, this is n minus 1 c r. We'll see this we are using in some other formula. Later I will come back to this. Now see the setup. So I have m and n sets of elements. I have m plus n. I have m plus say 10. I have 10 elements, out of which I have to make 6 or 4 sets of elements. 6. Once I select 6, 4 is already selected because once I group 6 elements together, balance is 4 elements. So 10C6 is equal to 10C4. So in place of 10, I am putting m plus n Cm or m plus n Cn. Both are same. Both are same. So as we select m elements, n elements are automatically selected. So m plus n factorial by m factorial, this minus this is n factorial. So the answer is m plus n factorial by m factorial and n factorial. Always remember here, these are of different numbers. They are not same numbers. M and n are different numbers. M and n are different numbers. Same if I continue. Suppose I have from 3 m plus n plus p items. I have to make subsets of m and p. Here 2, here 3. Same is extended. M plus n plus p, Cm. I am making n plus p items. M items first. I am making m items. M plus n plus p, Cm is m items groups. So once m items are selected, left is n plus p. So n plus p, I have to select n. So then automatically p is selected. So if I multiply this, I am getting same formula. These are same formula. M plus n plus p factorial, m factorial, n factorial, p factorial. So when I simplify it, what I am getting? M plus n plus p factorial by m factorial, n factorial, p factorial. Here the important thing is they are not of same number. They are different numbers. See, suppose 12 items to be grouped as 3, 4, 5. 5 plus 4, 9, 9 plus 3, 12. So then how I can group them 3, 4, 5? First I will select 3. So 12C3. This is 12C3. Then out of balance 9, I have to select 5. So 9C5. So when I multiply them, I am getting same formula. 12 factorial by 3 factorial, 4 factorial, 5 factorial. So this many ways I can group them in 3, 4, 5, 3 groups. Now let us see. Suppose if the group is equal, if instead of m plus n, both are mm, both are n. So n plus n is 2n. So 2n factorial by n factorial, same. But here, in earlier case, they can be arranged in, if there are two, they can be arranged in 2 factorial ways. That means what? Suppose set A is 1 element, set B is 3 element, which is different from set A having 3 elements and set B having 1 element. This is a different arrangement. Set A 1, set B 3 is okay. And set A 3, set B 1 is different from this. But when you come to the bottom one, set A also 2, set B also 2. So out of these 2 combination will become only 1 combination here. So like that we get 2 factorial. Only 1 common because equal set of equal elements. So 2n factorial by n factorial, 2 factorial. Suppose if 3 groups, if I have to make 3 groups, so 3n factorial by 3 factorial, n factorial, n factorial, n factorial, like that. So this type of combinations are reduced if the number is same. The number is same. Similarly, if we extend this, I want to make m groups. I want to make m groups, m equal groups. Understand? M equal groups. I have to distribute, suppose n and 12 apples into 4 persons. I have to distribute 12 apples to 4 persons. So each will get 3 apples. So I have to distribute m equal groups containing n elements. Each is, then what way I can make it? Total is mn. M groups, each n. Total quantity is mn. So mn factorial by m factorial into n factorial into n factorial into n factorial m times. Because there are m groups. So by way of this formula, they are m factorial. M factorial is for the repetition purpose. Here just the way we have used 2 factorial here, the way we have used earlier 3 factorial. So m factorial is repetitive to avoid repetitive because equal mean. So n factorial, how many times it is coming? Here it is 2 times coming. Here it is 3 times coming. Here it will come m times. So n factorial to the power of m. So what is the final ways? Mn factorial divided by n factorial to the power of m and m factorial division. This is reducing number of combinations because they are the same numbers. A set 2 element, B set 2 element, and B2, A2 is all same. So the 2 factorial is reduced. Here also, right, m factorial is reduced. We'll say this example. So 12 elements to be made to 4 groups of 3 elements each. So 12 factorial by 3 factorial to the power of 4 by 4 factorial. This many ways. Here I am assuming all the 12 apples are of different sizes. 12 apples are of different sizes. But they have to distribute it to 4 equal groups. Each will get 3 apples. So this is the combination. Okay. Now same thing we can apply mn persons. This is what we have written here. Mn factorial by m factorial, n factorial to the power of m. Because n factorial will come m times. What we have seen here comes n times. Suppose if they have to be allotted, we have to distribute to m persons. This is only we have made groups. We have made groups. How many groups? How many sets of groups can be made? So these are to be distributed to the 4 persons. So many groups are distributed to 4 persons. So there are 4 groups to 4 persons. How can I allot? One group can be 1 person, second group can be second person. Like that I have 4 factorial ways. I can allot them in 4 factorial ways. So mn by n to the power of order of m factorial into this m factorial because they have to distribute it. This is distribution. So m factorial gets cancelled, then I'll get mn factorial by n factorial to the power of m. See the difference between this example, and this example is here we are distributing to the 4 persons. Here we are only making it to 4 groups, M equal groups. Making into M equal groups. Here we are distributing to M persons after making equal groups. So the factorial will get cancelled out. M factorial. So the answer is n factorial number of M, the denominator. So these are the some examples. Let us see some more theorems on combinations. Suppose a condition has come, a plus 1 into a plus 2 into a plus n is equal to b plus 1 plus 2, then it is that a is equal to b. Suppose a is not equal to b, a is less than b. Then I put a plus n is less than b plus n. So when I put pi of a plus n, it should be less than pi of b plus n. N can be 1 to n. So that means the given expression will be wrong. So a has to be b. A has to be b. Now we have seen here, if NCR is NCK, then K can be either R or K can be either N minus R. Both are possible. As we know, NCR is equal to NC N minus R. Now let us understand this formula. N plus 1 CR is equal to NCR plus NC R minus 1. Suppose there are N plus 1 items and I have to select R items from this. How many ways I can select R items from N plus 1 items? N plus 1 C R. This is my left hand side. Now come to right hand side. This R ways I can select in 2 ways. One is having an element, one element, or not having that element. So if it has to have that element, one element K, then what is the leftover? N plus 1. 1 is already selected, so N are left over. What is R? R 1 is already selected, so R minus 1 left over. So N C R minus 1 ways. Here this contains that particular item and does not contain that item. So I have to select R items from N items. N plus 1, that 1 is not allowed, that K item is not allowed, so N. So N C R. So NCR plus this is NCR base. So NCR, so I can select having that item, I can select not having that item. This is NCR minus 1 is having that item. NCR is not having that item. So both together forms me N plus 1 CR. These are series of conversions. When we do examples, we can simply simplify the sum of NCRs. So NCR means what? This is does not have that item. N plus 1, that item is removed, become N. So I have to select R items from N. Here contains that item. So R already one item selected, R minus 1. N plus 1 already one item selected, N are remaining. So NC R minus 1. So N plus 1 CR is equal, N plus 1 is that including that item or excluding that item, both possibilities. I have to select R items. In R, it can have that K, it need not have that K. That can be present. And also this can be proved by expansion of NCR terms. We know NCR is N factorial by R factorial by R N minus R factorial. So we can do the mathematical expansion and also prove that it is tallying. This is what we have seen here. This is what we have seen. If it is K is 1, then K one object always included. So if K is 1, N minus 1, C R minus 1. If K is not included, N minus 1, C R. Same thing has come in the formula here. Instead of N items, I am first choosing N plus 1 items. Okay, let us go to this. Suppose there are PQR items are there. P of same kind, Q of same kind, R of same kind. Total P plus Q plus R items are there. So you have to select any number of items. That means you can select P0, Q0, R1. You can select R2. You can select R3 up to R item. You can select P0, R0, Q1, Q2 up to Q items. You can select P0, P1, P2, P3 like that, Q0, R0. Any combination. So number of ways of selecting any number of PQR items of same kind. How we can select? Suppose P items are there. I can have option of either not selecting it or selecting up to full. So I have option of P plus 1 options. I can select 1, I can select 0, I can select 1, I can select 2, I can select P. So we have P plus 1 options. Similarly, QQ plus 1 option, RR plus 1 option. When I multiply these, I'll get total number of ways of selecting these things. Suppose out of these, one option is such that P is not selected, Q is not selected, R is not selected, 0, 0, 0. That is one option. That the problem says you have to select any number. 0 is not, option is not allowed. So that means I have to reduce that option. So P plus 1 into Q plus 1 into R plus 1 minus 1. How we got? P of same kind, Q of same kind, R of same kind. So I can select any number. That is the point here. Any number. He's not telling R number. You have to select R from PQR. Suppose you have to select R from PQR. So P plus Q plus R, C, R. That is my simple formula. But here he is not telling you have to select only R. He's telling you can select any numbers. So this is how. So from first group we can select 0 to P. Second also 0 to Q, 0 to R. So we multiply by the principle of counting and we reduce this number. So now see another problem. Number of ways of selecting any number of items out of n different things. Here PQ are of same kind. Say P of same apples, Q bananas or pomegranates, but same kind. Here n different kind. N different kind. They have nothing is same. So in such case, how to select any number of items? I can select 1, I can select 2, I can select 3. So R is not R. Not restricted to R items. It can be 1, it can be 0, it can be n. Each item. So each item is having two options. Like I said, P plus 1. Each item is independent. Each item is 1. 1 can be selected, it can be selected or cannot be selected. It has two choices. Can be selected, cannot be selected. So like that, all items have 2 to 2 choices. So 2 to the power of n. But out of which we have to select at least 1. So 0, 0 option is cancelled out. So minus 1. All 0 option is cancelled out. 1, 0, 9, n minus 1 zeros, n 1, 1, no problem. But all zeros is, there is only one choice. So 2 to the power of n minus 1 ways you can select n dissimilar items. N dissimilar items. So depending on the problem, it has to strike to us whether they are dissimilar, whether they are similar. These things do apply in my selection of questions from given answer sheet question papers. I can select 3 out of 5 questions, 4 out of 5 questions, like that. We'll do problem solving, we'll understand this concept. Now I'll come to the other concept. Suppose before taking up this concept, let us understand this. Suppose 12 is there. What are the factors of 12? 2 square into 3 to the power of 1. 4 3s are 12. So 2 to the power of 2 into 3 to the power of 1. Okay, so it has how many divisors it has? It can be divisible by 1, divisible by 2, divisible by 3, divisible by 4, divisible by 6, divisible by 12. How I got this? So for 2 square, 2 is to the power of 2. So I can tell us how many ways I can select this 2. I need not select, or I can have 2 times. So total 3 times I can select this 2. It's like 2 repetitive, P times repetitive. So I can have P plus 1 possibilities. Here 1, so I can have 2 possibilities. So number of divisions, 3, P plus 1 plus into Q plus 1 is equal to 3 into 2, that is 6 divisors. This is 6 divisors. Here minus 1, why we are not doing? Because 1 into 1, 1 is also factor of my divisor of my item. So that's why we are not doing minus 1 here. So 6. So same thing is given as a concept here. Suppose n is having some factors P1, P2, Pk, and they have some powers n1, n2, nk. Here P1 is nothing but 2. N1 is nothing but 2. 2 square. 3 to the power of 1. So P1 to the power of 2 to the 2 square into 3 to the power of 1. Others are not there for 12. So for bigger numbers, so say 1000, we have more numbers. For 50,500, you have more numbers. So we have can be divided into basic factors. So they can be P1 to the power of N1, P2 to the power of N1. So how many divisors it have? P1 plus 1 into P2 plus 1 into N1 numbers, N1 plus 1 into N2 plus 1 into N3 plus 1 into Nk plus 1. So many divisors it is having. So if you are asked how many number of divisors, this is some type of problem. These are all part of combinations. How many combinations I can select? I can select 2 one time, I can select 2 2 times, I can select 3 one time, I can select 3 0 time and 2 2 one time. So these are the basically a combination concept. Combination concept. Let us see some solved examples here. So understand the concept in a better way. Committee of 4 members from 6 boys and 4 girls, such that at least one girl should be there. At least one girl should be there of 4 members. We have 2 methods. Total possibilities minus no girl selected. What are the total possibilities? 6 plus 4, 10, 10 C4. These are total possibilities. Selecting 4 from 10. So no girl should be there. What is the possibility of no girl? 6 C4. All 4 are selected from boys. So this we do in probability such problems. At least one girl, at least one red ball. So we see no red ball and divide from the universal set. Here also same thing. We are making a universal set. What is universal possibilities? 4 from 10. 10 C4. And what is that girl should not be there? So we have 6 C4. 4 is selected from 6 boys only. So 195. What is the second method here? I can have 1 girl, I can have 2 girls, 3 girls. So total 4 are selected, 4 girls. Because there are total 4 girls only here. I can select them. So 1 girl means there will be 3 boys. 2 girls means 2 boys left over. 3 girls, 1 boy left over, 4 girls. So I'm making this combination. 1 girl from 4 girls is 4C one way. 3 boys from 6 boys is 6C 3 ways. Similarly, 2 girls 4C2 into 6C2. 4C3 into 6C1, 4C4. So when I add this, I'm getting same 195. See this combination or permutation, we should be able to do 2, 3 methods so that the concept is clear. Either I can go through a rough method like this, basic method, 1, 2, like that as we have done here earlier. Here what we have done? 6, 7, 8, 9, 10. I have added all. Because at least 6. If it says at least 1, then I'll go for universal minus not having. But since 6 means I have added all 4 here. Same concept here. So these are the 2 methods to find out the selection of committee from this. Let us say, how many parallelograms can be formed when n parallel lines intersect n parallel lines? So for a parallelogram, how many lines are to intersect? 2 parallel lines M and 2 parallel lines N. If they intersect, we'll get 4 points. 4 points become one parallelogram. So then I have to select from M parallel lines 2 parallel lines, MC2 ways. I have to select from N parallel lines 2 parallel lines, NC2 ways. So MC2 into NC2, so many parallelograms can be formed. Same thing can be applied for triangle also. But here you see M and N are not parallel. If M and N are also parallel, then there is no intersecting point. They are not parallel. M itself, there are M parallel lines, N parallel lines, but M and N are not parallel. They are intersecting lines. So 2 lines from M, 2 lines from N will contribute one parallelogram, MC2 and NC2. Let us say, out of M points in a plane, P are collinear. P are collinear. Find the number of straight lines formed joining 2 points and number of triangles formed. So here, as I said here we are going parallelogram, here we are asked triangles and straight lines. So out of M, how many straight lines can be formed? MC2 lines can be formed. Because for a straight line, 2 points are required, but out of which P are collinear. So P cannot be formed. PC2 or options are deleted. PC2 options are deleted, but P lines, they form one line together. So MC2 minus PC2 plus 1. But out of which MP collinear points make only one line. P collinear points together making only one line. So I had to reduce MC2 to reduce by PC2 and added 1. Similarly for triangle, how many points are required? I need MC3. Out of which P are collinear. So PC3 are not possible. PC3 are not possible. So they don't make triangles. So this is the number of. So if all are not collinear, then I will simply put MC3. Triangles are formed. Okay, let us go to this. A teacher to take to park. 3 out of 10 in groups can be taken. How many ways each student can go to park? So 3 out of 10 in group can be taken. What is the way to select this? 10C3. 10C3. He says each student can go to park. So it should include, let us say one person is to be included in all these things. So I take out one, what is left out is 9. So 9C2. Other 2 can be selected from the other 9. So 9C2 ways, others are selected, and this person is also included in the list. So 9C2. Or if we say how many ways each student cannot go to park. So 9C3 ways. So when is removed from the list, 10 becomes 9. 3 buses are going 9C3. So that way. Okay. Each student can visit 9C2 ways. Let us say bus has an upper deck and lower deck. Out of 18 passengers, 3 children want upper deck, 4 people, old people want lower deck. How many ways they can be made groups of both decks, and how many seating arrangements? This is made groups or arrangements means permutation. Groups means combination. So he's asking both. Let us say out of 18 upper deck, 18 passengers, upper deck capacity is 10 and lower deck capacity is 8. So 3 children are already occupying upper deck. So how many balance seats are left out in the upper deck? 7 are left out. Here 3 children upper deck, 4 people lower deck. That means 7 people in overall have fixed their locations. So what is left over out of 18 minus 7, 11 people are left over. These 11 people have to be seated in upper deck in C. What is the upper deck capacity left over? 10 minus 3, 7 is left over. So if I make this 11C7 arrangements, 11C7 groups, automatically balance will go to my lower deck. Lower deck will be filled up. So how many ways I can fill up this? 11C7 ways. Because 3 plus 4 already fixed. 3 children upper deck, 4 lower deck are fixed. 7 are fixed out of 18. 11 are left out. Out of 11, I have to select balance 7 here. So M into N groups, M group, N group. So when I have selected M group, automatically N group is left. So, but number of arrangements, so I can go for 10 in the upper group. So 10 factorial, I can seat them. I can allocate 10 persons in the 10 seats in 10 factorial ways. 8 persons in 8 seats in 8 factorial ways. So this is the number of arrangements. Let us continue further problems attending on the combinations. Let us see. One type of examples in combination is exponent of p in n factorial. For example, in 100 factorial, what is the power of 3? So exponent of p in n factorial. Let us start with small. Let us say 10 factorial. This is a 10 factorial, which is 10 into 9 into 8 into 7 into 6 into 5 into 4 and 3 into 1. So when I am converting into the factorization, what I am getting 2 to the power of 8 into 3 to the power of 4, 5 square into 7 is my 10 factorial. My 10 factorial. So I factorized and brought in terms of prime numbers. These are all prime numbers, 2, 3, 5, 7 prime numbers. So automatically, if 10 factorial, one of the prime number cannot be more than 10. It is less than 10 only. So we have these 5 factors. Suppose we want to find out how this the powers are coming, 2 to the power of 8. So there is a short method. What is the short method? This 10 is there. I am dividing by 2. 2 5s are 10. So 5 is there. Again, I am dividing by 2. 2 2s are 4. So 1 is balanced. I am leaving it. 2 2s are 4. So again, I am dividing by 2. 2 1s are 2. 2 1s are 2. So total how many? 1. This is less than 2. So let us see. How many are there? 5 plus 2 plus 1. Total 8 are there. So this 10 factorial will have 2 to the power of 8. Let us see with 3. So I am dividing with 3. 10 factorial means 10. I am taking 10. So n factorial I have to take n. So 3 3s are 9. So 3 1s are 3. 3 plus 1, 4. So it will have 3 to the power of 4 in its factors. So 3 to the power of 4. So the exponent of 3 in 10 factorial is 4. The exponent of 2 in 10 factorial is 8. Like that. Let us see this one. I want exponent of 3 in 100 factorial. So I cannot write 100 into 99 into 98. This is a cumbersome process. So I use this method. So I am dividing by 100. 33 3s are 100. So 3 11s. 3 3s are 9. So 2 balance I am leaving it at. 3 1s are 3. When I add from 33 to 1, what I am getting? 44, 47, 48. So it has 3 to the power of 48 in its 100 factorial. So the highest power of 3 in 100 factorial is 48. I should not add 100 here because it is starting from 33. 100 is the 100 factorial which I am dividing. So when I convert this into a formula, what I am getting here? So the formula is n by p plus n by p square plus n by p cube, like that. Here you see n by p means 100 by 3, that is 33. So you are getting here 33 plus n by p square, 100 by 9. 100 by 9 is 11 plus 100 by 27 is 3. 27 3s are say 91 or 81. Beyond that, it goes beyond 100. So 25 4s are 100. So it goes beyond 81. So it goes beyond 100. So 3 times. 100 by p cube. 100 by p to the power of 4. So 3 to the power of 4 is 81 one time. So when I'm adding all these, I'm getting 48. So what is the formula? N factorial. What is the power of p in n factorial is n by p plus n by p square plus n by p cube, like that, till it comes 1. So let us see some example on this. Find exponents of 2, 3, 5, 7 in 100 and find the number of zeros in 100 factorial. If factorial is not there, simply 100 is there, I can find out factors. 100 is divisible by 4, 425. So 2 will be square only. 5 will be square only. These two are 0, 0. But it is not 100. It is 100 factorial. So and find number of zeros also coming in 100 factorial. 100 factorial we get 100 into 90 into 80 into 70 into 60. Almost there are zeros will come. Also 5 and 2 will come like that. So we'll see how to proceed. So 100 by 2 plus 100 by 2 square plus 100 by 2 cubed, 100 by 4, 2 to the power of 4. If we add this, 100 by 64, afterwards it's going beyond 100, so it's up to 64. 1 plus 3 plus 6 plus 12 plus 50. It's total 97. So in 100 factorial, I have 2 to the power of 97. So suppose 3, 100 by 3 plus 100 by 9, 100 by 27 plus like that. So just we have seen 3 here, around 48. So this 48 has come here. So 5, 100 by 5, 25, 125. 125 is greater than 100, so 0. So these two, 4 plus 20, 24. 7, we'll have 1 plus 14, 2. So 48 2s are 98, 2 plus 40. 7 cube is going beyond this scope. This is not 7 into 3, it is 7 cube, so going beyond 100. So it is 60. So 100 factorial can be 2 to the power of 97 into 3 to the power of 48 into 5 to the power of 24 into 7 to the power of 16, like that it goes on. So now what is being asked us? Find the number of zeros. Number of zeros means it should be a factor of 10. So it has 2 to the power of 97 and 5 to the power of 24. That means 2 to the power of 24 also is there. So 5 into 2, 10 to the power of 24 is there. So that means there are 24 zeros in 100 factorial. Okay. Now let us see what are the number of positive divisors of 1080. 1080 is simple, this is not factorial, this is 1080. I am converting into factors. 2 cube into 3 cube into 5. So 3 plus 1 into 3 plus 1 into 1 plus 1. These are the number of divisors. You have seen the formula now? You have seen here number of formula. This is number of divisors, n plus 1, n plus 2, n2 plus 1, like that. This is the number of, in the example also we have seen 2 plus 1 and 3, 1 plus 1, 6 divisors. 1, 2, 3, 4, 6, 12 are 12. So similarly here I have given p to the power of k1, q to the power of k2, r to the power of k3. So I can p1 plus k1 plus 1 into k2 plus 1 into k3 plus 1, 32 divisors. So 1080 is having 32 divisors. Notice the another example. If a student has to pass each of 3 exams, how many ways he can fail? So he can fail any one. He can fail 1, 2 pass, 1 fail, pass, fail, fail, pass, fail, pass, fail, pass, pass. So there are the different possibilities of 3 out of the 3 exams. So he can fail in 7 ways. Only PPP is the pass. So you can fail in 7 ways. That's how we calculate. So we know each exam you can fail or you can pass. There are 2 options. You can fail or you can pass. So 2 into 2 into 2. There are 8 ways. 2 cube minus 1 is the all pass. So we have 7. This is the formula we are using here. 2 to the power of n minus 1. See here. 2 to the power of n minus 1 we got here. 2, 2, 2, 2, n different objects. This one. Number of selecting any number of items, not restricted to or out of n different things. Here we have 3 different papers, each having 2 options. 2 to the power of q minus 1 ways. So each exam has 2 options, pass or fail. So we have total 8 options, out of which one is all pass. So the 7 ways he can fail. Suppose let us see this problem. 3 books of economics, 4 different books of maths, 5 different books of botany are available. They are not of same kind, they are different books. How many collections can be made if only one book of each subject is selected? So out of 3, I can select any of the 3. Out of 4, I can select any of the 4. I can 5, I can select any of the 5. Exactly one book of each. So the total possibilities is 3 into 4 into 5 is 60. Suppose if it is asked at least one book of each subject. Second condition is at least one book of each subject. That means I can select one economic book and this is 0. I can select 2 economic books and this is 0. I can select 3 economic books and this is 0. I can select 1 maths, others can be like that. So it goes on like that. So how to proceed for each at least one subject? If you take economics, out of 3 books, each book I can select or I need not select. They have 2 options for each book. So 2 to the power of 3 is the options available to me minus 1 because I have to select at least one book of each subject. It's not that one book of all. One book of each subject. So 2 cube minus 1. Similarly, 2 to the power of 4 minus 1. So each book has 2 options. So 2 into 2 into 2 into 2 4 times. So that 2 to the power of 4 minus 1, 2 to the power of 5 minus 1. Once I add all these, I'm getting selection of each book is, suppose selection of one group from all the group, any one from all. It cannot be 0. Earlier I said 1, 0, 0 is not allowed. So 1, 1, 1, 1, 2, 2 or 1, 2, 1. So at least one I have to select. So 0 option is ruled out. I cannot select 0 here. At least one book of each subject. Suppose if it is 0 is there, allowed one book out of all. I have to simply add 5 plus 4, 9, 12, 2 to the power of 12 minus 1. 2 to the power of 12 minus 1. So here is all each subject. So I have taken each possibilities and multiplied. 3 to 5 ways. Okay, it is slightly complicated, but take more time to understand this so that exam any type of such problems we can attend. Now 14 persons to be seated in a round table. Number of ways of seating 2 persons out of them who are not seated adjacent to each other. 14 persons in a round table, 2 persons should not sit adjacent. Where they can sit adjacent? A1, A2 is adjacent seats, A2, A3, A3, A4, A4, A5, like that. A14, A1, like a clock, wall clock. Instead of clock, we have now 14. Like a wall clock with 14 digits. So there are 14 ways. They can be seated adjacent. Totally, how many we can take them seating? 14 C2 ways. They can be seated in 14 C2 ways, that is 91 ways. This is not allowed. This is the number of possible ways. So the balance is number of ways they can be seated without having side adjacent seats. What's the second method? Suppose a person is seated at A1. Other person is, how many options he is having? He cannot be seated at A2. He cannot be seated at A14. He cannot be seated at A1. So 3 are gone out of 14. So 11 ways. So if the first person can be seated A1 to A14. So 14 into 11 ways they can be seated. But here some are getting repeated because when A person sits from A1 to A14, B also changes from A14 to A3 to A11. There is some superimposition. B also can be seated 14 places with having 11 options, for A having 11 options. So 2 are getting repeated. So by 2. So it's also 77. 14 into 11 by 2. 2 sevens are 14, 7 11s are 77. But this is slightly, it's only to understand the concept. You're getting 2 times repeated each seating arrangement, A to B and B to A. In permutation, this is allowed, but in combination, it is treated as 1. So by 2 factorial, when I take a 2 factorial, I'm getting 77. Let us see. This is simple. 10 into n C2 is equal to 3 into n plus 1 C3, find n. So simple calculation. 10 into 3, I brought it here, 10 by 3. N plus 1 C3 by n C2. N plus 1 C3 is nothing but n plus 1 into n minus 1 by 3 factorial into, this is n C2 is 2 factorial by n into n minus 1. When I am simplifying it, I am getting n is 9. So we have 12CR plus 1 is equal to 12C3R minus 5. Find R. So we have found NCR is equal to NCN minus R. So 3R minus 5 is equal to R plus 1. Or 3R minus 5 is equal to 12 minus R minus 1. Or R plus 1 is equal to 12 minus 3R plus 5. So when I simplifying, I'm getting two values of R, 3 and 4. That is 12C4. This is 12C4. This is 12C. 3's are 9 minus 5, 4. 12C4 is 12C4. Or 12C4 is 12C8 also. 12C7 also. 12C5 is 12C7. Because when I take 4, it becomes 12C5. 12C5 is n minus 5 is 12 minus 5, 7. 12C7. So we get 2 R's. So we should not limit to R plus 1 is equal to 3R minus 1. If we limit to this, we will not get full marks. R plus 1 is also equal to 12 minus 3R. We have two options. Both are satisfying this relation. So find the value of this. So 2 into 10C4, I am making 1 10C4 plus 1 10C4. 10C4 plus 10C3 is 11C4. 10C4 plus 10C5 is 11C5. So it becomes 11C4 plus 11C5. This becomes 12C5. This becomes 12C5. So we have seen this formula. N minus 1 CR plus NCR is equal to N plus 1 CR. NC R minus 1 plus NC R is equal to N plus 1 CR. So in a class of 30 students, how many chess games they can play with each other? So 30C2. 30C2 is 30 into 29 by 2, therefore 35. Each student can play with 29 others. So there are possibility of 30 and 29. Suppose this student is playing with other, means other student is also playing with him. So this is to be divided by 2. It is getting 2 times repeated. The way here it is 2 times repeated. Here also 2 times repeated. So by 2. That is 30C2. It also comes to shake hand also. Suppose each student has to give shake hand to others. So we need 2 persons to have a shake hand. So 30C2. So chess game or shake hand, any of 2. If 3 persons is there, then 30C3. So the C2 will automatically consider by 2 here. If you do rough method, 1 person can play with 29, 30% can play 13 to 29. There is a repetition of 2 times, 13 to 29 by 2. All this description is converted to one single formula, that is 30C2. Okay. Let us continue further problem solving. Let us see this. Find the number of ways of selecting 3 girls and 3 boys from 7 girls and 6 boys. Very simple. 7C3 into 6C3. Okay. Find the number of diagonals of a 12-sided polygon. So for a diagonal, you need 2 points. So 12C2 is many diagonals, but adjacent points cannot have, sides cannot be diagonal. So 12C2 minus 12, that is 54 members. If you see here, suppose n-sided polygon is there. So NC2 is the number of diagonals minus n sides. If you simplify it, n into n minus 1 by 2 minus n. That is n into n minus 1 minus 2n by 2. N into n minus 3 by 2. This is the formula for number of diagonals of a n-sided formula. So this is how the formula has come. N into n minus 3 by 2. So let us go to next problem. Suppose n persons are sitting in a row. Find the number of ways students can sit together. Earlier we have seen cannot sit together. In this problem, they they are not seated adjacent in a round table. But here, they are in a straight row, sit together. We have only 9 options. A1, A2, A2, A3, A9, A10. A10, A1 is not possible because they are not in round table. So they are sitting in a row, only 9 ways. It's a simple problem. Sometimes this simplicity we may distract seeing the problem. So a set has 12 elements. Find the number of subsets having at least 3 or at most 3. The two conditions. One is at least 3, another is at most 3. So at least 3. So 12C3, 12C4, 12C5 up to 12C12. Adding all. Otherwise, second method. Each element can be selected or cannot be selected. 12 elements, each can be selected, cannot be selected. There are how many methods? 2 to the power of 12. Out of which we remove the 3 selections. These two selections. 12C0, 12C1, 12C2 are the ways of selecting 0. So instead of selecting 1, instead of selecting 2. So when I do minus, so I'll get at least 3 selection as 4017. So both methods. This is a rough method. This is we know 2 to the power of 12 is the way they can be selected or not selected. Out of which I am removing up to 3, less than 3 options. So for at most 3 means maximum 3. So simple 12C0 plus 12C1, 12C2 plus 12C3. Here I am adding 12C3 also because up to 3 it is allowed. So 299 ways. Okay. Let us see this. Find the number of ways of giving 4 similar coins to 5 boys. Each can be given any number. So each boy can be given 1, 2, 3, 4, any number. 4 coins are to be given to 5 boys. Now these 4 coins can be made different groups, can be made to one group, can be made 2 groups of 1, 3, can be made 2 groups of 2, 2, also 2 groups of 3, 1. 1, 3, 3, 1 is different group. So can be made 3 groups of combined 1, 1, 2, 1, 2, 1, 2, 1, 1, or can be made 4 groups 1, 1, 1, 1, 1. So if it is all made to one group, say all 4 coins in one box, I am giving to, it can be given to 5 persons, it can be to any of them. So 5C1 base. If they have 2 coins, 2 groups, 1, 3, I give 5C2 base. Again 2 groups, 5C2 base. Again 2 groups, 5C2 base. Now I have 3 groups. 3 groups to be allocated to 5 boys, 5C3. 5C3 base. Again 3 groups, 5C3 base, 3 groups, 5C3 base. 4 coins to be allocated to 4 groups. 4 to allocate to 5. So means I have to give 5C4. So when I add all these, I'm getting 70. So this is the way we distribute 4 similar coins to 5 boys if any number can be given to anybody. Otherwise, if you simply say you select 4 similar coins, 4 coins from 5 coins group, so 5C4. But it is not that. It is actually complicated. Boys different. We are making different groups with 4 coins because any number. So I have 4 group. I have 1, 3, 2, 2 group, 3, 1 group. This is a 2, 2 groups. These are 3, 3 groups. 3 groups. Now, let us see. There are 8 railway stations. How many ways a train can be stopped at 3 of these stations such that no 2 of them are consecutive? Suppose there are 1 to 8 stations. So what are the various combinations? Suppose the train stops at 1. So next available is 3. So it cannot stop at 2. So after 3, it cannot stop at 4. It can stop from 5 to 8. So how many options are here? 5 to 8 means 5, 6, 7, 8. 4 options here. Suppose it starts from, instead of 3, it stops at 4. Then we have 6 to 8. So 6, 7, 8, 3 options. If it starts up at 5, then we have 2 options, 2. So 4 plus 3 plus 2 plus 1. It cannot stop at 7 because it has to stop at 3 stations. 1, 7, 8 is not possible. So it cannot, there is no 9th station. So it cannot stop at 7. So I've taken all possibilities. 3, 4, 5, 6. So total 10. So I'm taking a condition that is stopping at the first station. Now let us say it's stopping at the second station. It's not stopping at the first station. Again same 2, 4, 6 to 8, 2, 5, 7 to 8, 2, 6. There are 6 ways. If it is stopping at third station, we have 3 ways. If it is stopping at fourth station, we have only 1 step. So it cannot stop at fifth station onwards. Fifth if it starts, then what is the next is 7th, next is 9th, the 9th is not there. So it is not possible, it is not there. So when I'm adding all these things, I'm getting 20 ways. If you see another way, out of 8 eligible stations, we have 8 minus 3 plus 1, 6 stops are possible. So when I'm saying 6, say 3, I'm getting 20. 6 into 5 into 4 plus 6. 5 4s are 20. So out of total eligible stations, if we were able to better understand this, eligible stations are minus 3 plus 1. Let us see further divide. Let us see. Same. Number of ways of selecting any 3 stations, 8C3. Okay. Number of ways of selecting 3 stations which are consecutive. Consecutive means 1, 2, 2, 3, 3, 4, 5, 6. 3 stations consecutive. 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 7, 6, 7, 8. There are 6 ways. So number of ways of selecting 3 stations in which 2 are consecutive. 2 are consecutive means suppose 1, 2. 1, 2. 1, 2 is consecutive. I have 4 to 8 options. 2, 3 is consecutive. I have 5 to 8 options. 3, 4 is consecutive. I have 6 this many options. 4, 5 is consecutive. 5, 6 is consecutive. There are 15 ways. If you go from behind also, 7, 8 is consecutive. 5, 6. Next is 7, 8 is consecutive. I have 1 to 5 options. 6, 7 is consecutive. I have 1 to 4 options. So here, out of 3 stations, 2 are consecutive. Around 30 numbers. Out of 3 stations, all are consecutive. 6 numbers. So from 8C3, if I minus these 2, I am getting 8C3 minus 30 minus 6, 20. So we can see this is one method. This is another method. So you can able to understand this. For me also, I could not understand this, but this is one method. Toppers are given this method. This is our simple method. So 3 methods are given here. Let us see. We want to find a committee of 5 members so that Indians will be majority from 6 Indians and 5 Americans. So 5 members, Indians will be majority. So first is, I can take all 5 from Indian people, 65, no American. I can select 4 and 1, 64 into 5C1. I select 3, 63 into 5C2. I can select 2, 62 into 5C3. It's not possible because here 62 members will be reduced. It should be majority. So it is stopping at this point. So when I'm adding, I'm getting 281 ways. Okay. Now, suppose there are 3 sections. A, B, C contain 3, 4, 5 questions. In the section A, 3 questions. Section B, 4 questions. Section B, C, 5 questions. Find attending 6 questions from them. At least 1 from each subject. It should be 1 from each. So there you can have 2, 3 methods. One method is how many ways 6 can be selected from 12? 3 plus 4 is 9, 9 plus 5 is 12. 3 plus 4 is 7, 7 plus 5 12. So there are 12 C6 ways. Out of which, suppose I don't want to select from section A. What is the probability if I don't want to select 6 questions without having section A? So what is section BC is 5 plus 4, 9. So 9 C6 ways. Similarly, here 8C6, here 7C6. These are the ways where it won't have section A. It won't have section B. It won't have section C. So I am selecting from all possibilities, no 0 from section A, 0 from section 0 from section C possibilities. I am getting 805 ways. Otherwise, you see, section A I have selected 1 question, section B 1, section C 4, total 6. 1, 2, 3, or 1, 3, 2. Again, you go 1, 4, 1. So, like that, you do physical tabling. Then what you got? From A, I have to select 1. So, from 3 questions, I have to 3C1, 4C1 into 5C4. 3C1, 4C1 into 5C4. This is the first combination. Second one, 3C1, 4C2 into 5C3. Last one, 3C3 into 4C2 into 5C1. So when I'm adding all, I'm getting 805 ways. This is a rough understanding method. This is what we know. Whenever it says at least 1, we take all and we minus none. So I'm taking none options and minusing from all options. This is a better way of understanding the problem whenever at least is given. Whenever at least is given. Let us see. Find the number of ways in which 12 things can be made into 4 groups and distributed to 4 different persons. We have seen 4 groups, means 3, 3, 3, 3. 4 groups. 12 things are made to 4, 3, 3, 3, 3 to distribute to 4 persons. We have seen 12 factorial by 3 factorial to the power of 4 into 4 factorial. These are 4 groups, m factorial, n factorial to the power of m. So these many groups can be formed. This many groups can be formed. But if you have to distribute to again 4 groups, 4 different persons into 4 factorial way, 4 factorial, 4 factorial cancel. So 12 factorial by 3 factorial to the power of 4. So this is the answer. So some problems are given here. You have to get exposed to more and more problems so that your concept will be clear. Mostly for such problems you have to get exposed. At least 1 or these are all simple direct formula submission. This is at least 1. This is a selection 3 stations, like that. Some complicated, you should do more practice.